We introduced functions in our last video, which we can think of as a generalization of the idea of a computer program. Functions take in input from one set called the domain of the function and map it to output in another set we call the codomain, according to some kind of rule. That rule might be a formula, a code snippet, a set of verbal instructions, or a picture. But the mapping takes place so that every element in the domain maps to exactly one element in the codomain. So a valid function never takes an input and splits it into two different outputs. But what happens if a mapping does the opposite, sending two different inputs to the same output? Is this allowed? What happens if it is? That's the subject of this video. First, let's be clear that valid functions can send two different inputs to the same output. In fact, many functions we use in real life do this. Consider the function from the set of all students at your university to the set of all days of the year, which maps a person to their birthday. This is a valid function because every person has a birthday, and nobody has two birthdays. So the function does produce an output for each person, and it doesn't split inputs by giving a person two birthdays. But two different people could very well map to the same birthday, and this doesn't make the function invalid. You might say that this function has collisions, two inputs from the domain that collide in the codomain. But not all functions have collisions. For example, look at the function that maps students at your university to the set of all student ID numbers at your university. If this function had a collision, it would mean two people have the same student ID, and generally speaking, that's bad. We'd like to distinguish valid functions that have collisions from those that don't, because the existence of collisions has real-world implications, as we just saw. So we're going to say that a function where two different inputs never map to the same output is injective. More formally, we say a function f from a to b is injective if, for all elements x1 and x2 in the domain, if x1 does not equal x2, then f of x1 also does not equal f of x2. This is the formal way of saying there are no collisions. A pair of distinct inputs must always map to a pair of distinct outputs. Let's look at some examples and non-examples. The ID number function is, we hope, injective. Again, because if you take any two different people and plug them in to this function, you should get two different ID numbers. This function, given as a table from the set 1, 2, 3, 4 to the set x, y, z, t, is also injective because you can look at the table and see that no two different elements in 1, 2, 3, 4 map to the same element in x, y, z, t. The function f from the natural numbers to the natural numbers, given by the formula f of n equals 2n, is injective too. Why is this? This time we can't use a table because both the domain and codomain are infinite. So let's give a rigorous explanation using the definition of injective. That definition, remember, says f is injective if for all x1 and x2 in the domain, if x1 does not equal x2, then f of x1 does not equal f of x2. Note that conditional statement. I'm actually going to use the contrapositive of the statement, which, remember, is logically equivalent to the original. The contrapositive would say that for all x1 and x2 in the domain, if f of x1 does equal f of x2, then x1 does equal x2. So let's pick any two natural numbers from the domain and call them a and b, and just suppose that f of a equals f of b. Apply the function on both sides to get 2a equals 2b. Well, if that equation is true, we can divide off the 2's to get a equals b, and that shows that the function is injective. The definition has been satisfied for some random choice of a and b. If their outputs are the same, then their inputs must also be the same. So proving that a function is injective is a matter of showing that all pairs of different elements in the domain always map to different elements in the codomain. Examples won't do. This is a universal statement that has to be shown for all pairs of points in the domain. Now here are some non-examples. That birthday function from earlier is a good non-example because in a group the size of your university student body, it's nearly 100% likely that you can find two people with the same birthday. Here's another function from the set 1, 2, 3, 4 to the set x, y, z, t that you can see as non-injective because there is a collision. 1 and 2 map to the same element in the codomain. And the mathematical function f from the integers to the integers, given by f of n equals n squared, is not injective because f of -1 and f of 1 both map to +1. So showing a function is not injective is a matter of finding an example of two distinct elements in the domain that map to the same element in the codomain. However, notice in that previous example, if we'd used a different domain, for example, f mapping the natural numbers to the integers, with the same formula, this function would be injective. Because if n were the domain and not z, let's suppose I had two natural numbers a and b such that f of a equals f of b. Then applying the function gives me a squared equals b squared, which gives me a squared minus b squared equals 0, which means that a plus b times a minus b is 0. This means either a plus b is 0 or a minus b is 0. The first possibility gives me a equals -b, and that's only possible in the natural numbers if both a and b are both 0 themselves, because a and b are natural numbers, not just any integer. And in the second equation, we have a equals b. So in either case, a and b are equal to each other. So that means the function is injective if you use the natural numbers as the domain. In this video, you've learned about injective functions, what the definition is, and also the contrapositive of the definition is, seen some examples of injective functions and some that are not injective, and seen examples of how to argue that a function is injective and how to argue that it's not injective. In the next video, we'll look at a similar property for functions involving situations where the codomain and range are equal.